Okay, video started. Yes, so we have a test on Wednesday. That's test 3. Whenever somebody's like ringtone rings, do this, like imagine it's a scene in a movie and that's the background music, and imagine what would happen in that scene, you know? Well, no, I mean, we're in a classroom though, so. Yeah, right. But don't do it out loud. Okay, so exam 3 is Wednesday, the 29th. And it's up through linkages. Also, the assignment is due on Wednesday, up through, linkages stuff. If you want to turn that in Friday or Monday, that's fine with me. But you need to understand that stuff by then anyways. So today I would be happy to answer questions about that. If you'd like homework questions or general linkage questions. When we run out of questions, I'll go on to rotating coordinate systems.
Can I make a proposal?
Yes.
Okay, so we're probably only going to get through one question today.
Okay.
So we have 2 objectives. We can either finish a homework question or finish, like the hardest homework question, or finish a homework question that will be on the test. And there's 5 on here that don't have solutions posted.
Okay.
That is one of them.
Can
we choose out of those 5 which one will be on the test and do it together?
No.
Do you guys think? Yeah?
No.
I've made a plan.
No.
So number 9. I don't think that was going to be on the test. It's too crazy.
What is it? I see what you mean.
You know what I mean?
Okay, so let's assume that everyone's fairly good with the rigid body part of it, and let's just talk about constraints. And then we can do a couple of problems. Okay, so that was a terrible plan.
It's only really serves us.
So, yeah. Let's see. So what do we know about this? Well, after the rigid body kinetics, and let me draw the picture, I guess. We have a member like this. It's connected to the ground by a pin. And it's connected to another member that's perpendicular to it, like this. We'll assume that those two are the same height. And it's connected to a disc like that. So we'll call this member 1, 2, 3. 1, 2, 3 pin joints, yes. But this is not connected to the ground. This is only connected to the disc. This is the one that's connected to the ground. A pin joint down here. Right, the middle one is to the ground. That's a pin joint. No, that's right. It's not. So after the rigid body kinetics, how many equations do we have? We have 3, 6, 9 equations. And how many variables are we going to have? Well, that's going to be determined by yeah, you're right. Two have a one, two. Hey, yeah, right. Two have fixed points. Yeah. So you have one equation for one equation for three, and three for two. So yeah, five. That's one from one from three, three from two. And how many variables are we going to have? So you can figure that out by figuring out how many joint constraints we're going to have. We're going to have one joint constraint that says, okay, let's name these connections. So here's A, B, C, and D. So we're going to have one acceleration requirement that says the acceleration at B according to 1 has to equal the acceleration at B according to 2. And then we're going to have another one that says the acceleration at B according to 2 matches the acceleration at B according to 3. So how many equations is that? Two for each of those because it's a 2D problem. So we're going to have 4 constraint equations. So we must have 9 variables. Constraining based on a joint that won't have vertical or horizontal acceleration? You mean like a joint that, so you could have something like where you had a pin and slot joint where or a roller where this was at an angle. I'm not going to give you that, but it's not too hard, too different to do it. You just take a dot product of the correct, you take a projection of your acceleration vector at that point onto the correct direction, just using a dot product. It gives you one equation. Well, we're not going to do that. We have to stop somewhere, I guess, with how complicated these get. Okay. You brought it up. I wasn't think about it, but now I can't stop. Okay. Yes. Yeah, and it always has to be accelerations. It can't be velocities because of the nature of what a constraint equation is. You know, all that we're getting from Newton's laws are loads and accelerations and angular accelerations, and so we need our constraint equations to relate those things. You know, so that's why we do it with acceleration. Although you could come up with valid equations involving velocities, they just wouldn't help us solve the system we want. Okay, so the first one we have to do is relate the accelerations at B. So first one says acceleration of B according to member 1 is equal to the acceleration at B according to member 2. We have to figure out these angles. Is there some kind of easy, let's see, middle rod, 0.9. Yeah. So we know it's a right triangle with and we know it's 1.2, that diagonal length, and then 0.9 here. Oh, so it's a 3, 4, 5 triangle. So this is 1.2. This is 0.9. So this is 1.5. Does that help us? So this length is 1.5. And what are the angles in a 3, 4, 5 triangle? I forget. Well, I guess we just have to do the trigonometry. It's not. It's some funky thing. Okay, well, this angle is the arc tangent of 3 over 4. You're all like, good to know. And then you just go back to texting your friends. Calculate it for me. Yeah. Okay, and then so this one's 90, so this one is 53.13. Okay, so we'll first calculate the acceleration according to member 1, AB according to 1. So the circular motion is this. And so the acceleration of B, does this thing have an angular velocity at this instant? No, because I would have had to figure out ones that matched. Oh, it does. Oh, you have to figure it out. Oh, that's brutal. Yeah. You have to figure out the angular accelerations of all those. You have to figure out the angular velocities of all those bodies based on what's allowed by the linkage. Okay, let's do it. Yeah. So here's a tricky issue. You need to figure out the angular velocities of the bodies of body 1 and body 2 based on the angular velocity of 3. Why do we need the angular velocities? That's right, because the acceleration of B, because the acceleration of B is equal to the watermelon equation. And so these things are needed. Yep. Is there anything special about the Yeah. Yeah, well, that's the center of mass, and we have a variable representing the center of mass, so we can just call it A2. We already have a variable representing the acceleration of the center of mass. So that's a bright spot. Yep, that's a good thing to notice. Okay, so how are we going to get these angular velocities? So you asked, what if you just treated it as angular velocity equal to 0? you'd get the wrong answer. But what we have to do is we have to do the same thing that we're doing with the accelerations now. We can do with the velocities to figure out what the angular velocities are. So to get the angular velocity of 2, so for omega 2, what? Nope. So for omega 2, here's what we know. The velocity at d according to 2 is equal to the velocity at d according to 3. Okay, so that's the idea. According to 3, no, we're not assuming that. So yeah, let's just sort of think through it. 3 is the easy one because we know the angular velocity of 3. So, right. So not acceleration. Velocity of d is equal to omega of 3 crossed with the r vector that goes from the center of that circle to d. I'll just write it like that. And we know all these things. So this one is not so bad. This is 0, 0, negative 5. That r vector is from the center of the circular motion to d, and the radius of that circle is 0.5, so that's 0, negative 0.5, 0. And so the velocity of d is negative 2.500. That's according to 3. Now, according to 2, how with accelerations, how do we do this? You know, with accelerations for this constraint equation, we assume d is in circular motion around the center. We calculate that relative velocity of d, then we add it to the velocity of this. But this time we don't know the acceleration of the center, so we're going to have to do like 2 relative motions to go from here. You know, we're going to have to express the velocity of this point in terms of the angular velocity of body 1, and then add that to the relative velocity of this. We're going to get an expression that has omega 1 and omega 2 in it, and that's what we're going to solve for. Yep.
Why wouldn't it just be a negative 2 cross the r vector from d to?
Because that's not a pure circular motion. This point is moving. Yeah, this point here is moving. And so we have to do it as relative motion. So the way to think of it is like this. Yeah, so like the acceleration of velocities, yeah. The velocity of b is equal to the angular velocity of 1 crossed with r going to b. And then the velocity of d relative to the ground is equal to the velocity of d relative to b plus the velocity of B relative to the ground. That's this one. This one is circular motion.
And then we
Eventually, so what we have is that the velocity of B is equal to omega 1 cross RB plus velocity of D relative to B is omega 2 crossed with that R vector 2D from B. That's not so bad. I guess that's all it is. And then we're going to set those two velocities of B equal to each other. And that'll give us two equations to solve for those two unknown angular velocities. So VB is equal to 0, 0, omega 1 crossed with the vector going from A to B. And that is 1.2 times cosine and sine of 36.87. Can someone calculate that? Yeah, 1.2 times. Five? Yeah, right. Yeah, exactly. And then omega 2 is 0, 0, omega 2. And the vector 2D from B is, you could think of that as 0.9 times cosine and sine of 180 minus 53.13. Yeah. We're just trying to get the vector that goes to from. Yeah.
negative 0.5.
Let's see. Negative. The x component needs to be positive. 2b from d. Oh. I think maybe just negative of what you're getting there.
Yeah. Should be the right.
Magnitude.
Yeah, it should be the negative one.
Okay. So what do you get here for this? Okay. And can someone calculate those?
Minus 0.72.
Okay.
0.96 plus 0.54 omega 2.
Okay. And then 5 again.
Yeah.
Okay. So VB, the two VBs have to match. So our VB, no, our two. This is VD. This is all V. This thing should all be D. This is what we're trying to find, VD. We all want VD. Negative 2.50. Negative 2.50 is equal to 0.72 omega 2 minus 0.72 omega 1, 0.96 omega 1 plus 0.5 for omega 2. That's a system of two equations for two variables. You can solve for it. So negative 0.72 omega 1 plus 0.72 omega 2 is equal to negative 2.5. And the second one is 0.96 omega 1 plus 0.54 omega 2 is equal to 0. Can someone solve that system? Okay. Whew. So those are the omegas. And now we can do the constraint equations. Okay, so AB according to, this is member 1, AB is equal to alpha 1 cross R 2B from A plus omega 1 cross quantity omega 1 cross R from B 2B from A. So AB is equal to 0, 0, alpha 1 crossed with, we already got that R vector from 2B from A. That was 0.96, 0.72. Plus 0, 0, 1.25. Cross quantity 0, 0, 1.25. Cross 0.96, 0.720. And then according to member 2, the acceleration of B relative to the ground is equal to the acceleration of B relative to the center of mass of 2 plus the acceleration of the center of mass of 2 relative to the ground. This one's your A2. Yes, that's right. Yep, you're right. So this goes away. And so the acceleration of B is just A2. Because because B is the center of mass of 2. Okay, so now you just have to set this expression for the acceleration, calculate that, set it equal to this, and those are your first two constraint equations. And then there's one more constraint equation at D. So these are constraints 1 and 2. And now we have to say that the acceleration at D, according to 2, is equal to the acceleration of D according to 3. So first, let's do member 2. The acceleration of D relative to the ground is equal to the acceleration of D relative to the center of mass of 2, plus the acceleration of the center of mass of 2 relative to the ground. This term is the acceleration, this is A2, that's one of our variables. And this is circular motion around the center of mass of 2. So the acceleration of D, according to member 1, is equal to alpha 2 cross the vector 2D from B plus omega 2 cross quantity omega 2 cross R dB plus A2. And we know those omegas now, and we know those R's. And I'm just going to leave it like that. And then member 3, the acceleration of D is equal to alpha 3 cross R 2D from the center plus omega 3 cross quantity omega 3 cross R to the D from the center plus A2. Omega 3 was the one that was given, yeah. Because of relative motion. So I'm just putting it all together here. To calculate the acceleration of D relative to the ground, relative motion says it's equal to acceleration of D relative to the center of the circle plus the acceleration. Oh, yeah. This is, yeah, right. This is A3, yeah. Thank you. So this, you don't need any of this. You don't need relative motion because the center is fixed. Oh, we did number 2. I just got my numbers all messed up, sorry. So this is now member 3. And according to member 3, we don't need any relative motion because it has a fixed point. So according to member 3, the acceleration of D is just circular motion around the center of the circle. Yeah, that's those are supposed to be 3s, and these are. Oh, dang it! Okay. Yeah. Okay, so all the relative motion stuff for member 2, we did need that. Okay, Number 2. Now that's number 2. That's good. Yeah. Okay. Right. There's no relative motion in member 3. There's just circular motion around the center. Yeah, exactly. And now you set these two accelerations equal to each other, and you know, AD equals AD gives constraints 3 and 4, and now you're done. The only thing, so that problem is just like the other problems, except that I think it's the only one we do that has 3 bodies, and it's also definitely the only one we do where you have to calculate angular velocities based on what's given. Any other questions about that one? If you, on your paper, say you are in class at this instant listening to what I said, and you can set those angular velocities equal to 0 if you want. Well, we already have them, but you know, calculating those velocities is the hard part of, you know. Yeah, we did it. Yeah, but you can set them equal to 0 if you want. That one's pretty. Okay, is there another one you'd like to see the constraints for? Okay. Just 2. Just, yeah. Okay, number 8. So you have 2 members that make an X. They're connected at their midpoints. This angle's 40 degrees. All the lengths are the same, so this angle is also 40 degrees. You have a 500 Newton force here. M1 is equal to M2. 1 point is equal to 20 kilograms. L1 is equal to L2 is equal to 1.5 meters. That's right. Okay, so after Newton's laws, after the rigid body kinetics, we have one equation for, so this is 1, this one's 2. Remember, 1 has a fixed point. So we have one equation for body 1, 3 equations for body 2. So 4 total equations. How many constraints are we going to have? Yeah. If I call this A, B, C, there's going to be 2 constraint equations at B because those accelerations have to match. There's going to be 1 constraint equation at C because it just can't accelerate vertically. That's what the slot does for that pin. And so we're going to have 7 variables. We're going to need 3 constraint equations. So the first one, at B, this is the one you pretty much always have this type of constraint. Acceleration of B according to 1 is equal to the acceleration of B according to 2. Remember 1, there's no relative motion because it has a fixed point at A, so the acceleration of B is just equal to alpha 1 cross r vector 2B from A plus omega 1 cross quantity omega 1 cross r 2B from A. And this one, it doesn't say anything about the angular velocity, so let's say that it's at rest at this instant. So the omegas are both equal to 0. All right, so that's B according to member 1. And then according to member 2, the acceleration of B is equal to, so this is B relative to the ground, is equal to the acceleration of B relative to the center of mass of 2 plus the acceleration of the center of mass of 2 relative to the ground. And this is 0 because B is the center of mass of 2. So the acceleration of B according to member 2 is just equal to A2. And so set this expression equal to A2, and that's your first two constraint equations. Any questions about that one? And then the other one we need is at C.
Compared to the ground for the right-hand side of the equation, is it possible to have center of mass of something only in one of those two that you're adding up? So the center of mass, is it possible to have that in only one of those accelerations that you're adding up?
That you're setting equal to 0?
Yeah.
Yes. Usually, one of those will have a fixed point. If you just have two bodies in the system, usually one will have a fixed point and one won't. So then, yeah, in your expression, they'll only be the center of mass of, the acceleration of the center of mass of one of those bodies will be in those equations. And then the second constraint says that the acceleration of C, y component is equal to 0. The acceleration of y, or the acceleration of C, relative to the ground is equal to the acceleration of C relative to the center of mass of 2 plus the acceleration of the center of mass of 2 relative to the ground. This is A2. This is circular motion. around the center of mass of 2. And so the acceleration of c is equal to alpha 2 crossed with a vector going 2c from the center of mass of 2 plus omega 2. Oh, well, this all goes away because we're assuming it's at rest. Plus a2. A bunch of stuff went away here. This stuff all went away because we were at rest at that instant. And now from this expression, the y component is equal to 0. And that gives your third constraint. Then you can solve it. Any questions about that one? Okay, that's all. Test on Wednesday.